For the n-Lorem Foundation, N of 1 doesn't mean alone because every patient matters. Hope for nano-rare patients and their families has never been more within reach. Visit n-Lorem.org today to donate and make hope possible.
Join us at the 2024 Nano-Rare Patient Colloquium hosted by Biogen on October 30th through 31st in Cambridge, Massachusetts. At this event, n-Lorem will review the Foundation's progress, present case studies, and host discussion panels with members of the nano-rare community. You'll also have the opportunity to connect with supporters, physicians, advocates, and, of course, patients and their families. We hope to see you there. Visit n-Lorem.org to register today.
Hello and welcome to the n-Lorem podcast series, a series that focuses exclusively on patients now referred to as having nano-rare mutations. I'm Stan Crook, and I'm the founder, chairman, and CEO of n-Lorem. n-Lorem is a nonprofit foundation that I initiated in January of 2020. Our mission at n-Lorem is to take advantage of the technology we created at Ionis Pharmaceuticals, Antisense Technology, or ASO technology, to discover, develop, and provide experimental ASO treatments to nano-rare patients, and to do that for free for life. It is often said, and it's often said because it's true, that knowledge is power. And today, I plan to discuss how the knowledge that we're gaining at n-Lorem will do vastly more than providing benefit to nano-rare patients and families. And of course, that itself, that is, helping nano-rare patients, is an extraordinary and sufficient dream that we are realizing every day at n-Lorem. But the knowledge we're gaining is teaching us about how tiny changes in a gene can cause massive changes in the cellular networks that support health and result in what we refer to as disease. And that information is helping already identify new therapeutic targets for many diseases, not simply nano-rare diseases, and it will change the way we think about health and disease altogether. We're taught to think of health and disease as two separate entities, but in fact they're not. Each is simply a specific biological state or phenotype. Remember, a phenotype is simply the summation of all of the various characteristics in all of your cells combined together to give a set of characteristics that you express at any particular moment. Whether you could perceive yourself as healthy or whether you perceive yourself as having a disease, you're really just measuring a phenotype that you're expressing at that moment. It's important to realize that health and disease are simply different summations of the same biological systems and processes. So they're the same basic fabric, just a different set of expressions of what's going on in your body. So when we see a patient with a phenotype that we recognize as disease, we're actually seeing a human being who has undergone millions and millions of molecular steps that then result in him no longer being able to express a healthy phenotype. And so even at the earliest stages of any disease we know about, millions of molecular steps have shifted that healthy phenotype to what we recognize as a disease over some period of time. So key point, health and disease are simply two phenotypes. Both reflect the integrated output of millions of molecular events, and both part of the human fabric. The two most used words in medicine are health and disease. Now, if you look up the definition of health, you will find several definitions. The most commonly used definition of health is the absence of disease. To define something as important as health as the absence of something bad is, to my way of thinking, very unsatisfying. Another definition of health is simply the ability to cope with day-to-day life. That, to me, reduces health to the ability to make it through another day, which is, I think, truly a pessimistic view of what health is. So I prefer my definition of health. Health, as I think of it, is the robust ability to respond to the environment and to look forward to with confidence and optimism to the future. The definitions of disease that we accept are simply archaic descriptions of what a patient looks like when that patient is symptomatic enough to seek medical care. And we know, once again, that for that patient to actually come to have those symptoms, millions of incremental steps had to take place at the molecular level before all of that happened. For example, psoriasis was defined as dry, itchy, scaly skin in the 1600s, and we still describe psoriasis in that way, and similarly for all other diseases. So in my view, these traditional definitions of disease have served their purpose. And to a large extent, I think they're getting in the way of real progress. We should discard them in favor of molecular mechanistic definitions of disease. Key point, health is a phenotype that supports a robust responsiveness to the environment and enables a person to look forward with optimism and confidence to a future. Before we actually get into the meat of things, I want to lay the basic foundation, or a basic foundation, on which we can build a better understanding of what I mean by knowledge is power, especially when it relates to health and disease. And I'll do that by simply summarizing some key terms for you. And the first one I want to talk about is the scientific method. The scientific method is sort of a modest-sounding phrase, but it is a way of thinking that has reshaped our planet. It's changing our solar system, and it may someday enable us to reach the stars. It is of fundamental importance, and it is the basis of the modern world. It is the basis of the modern world, which is something to think about when you think about it. I mean, a way of thinking enables the modern world. And it's often attributed to Greeks, in particular Democritus and Aristotle, but it is a concept that arose in many cultures, many ancient cultures, at roughly similar times in the evolutions of cultures. And so it's a concept that requires some maturation of cultures before you actually see it in place. At its simplest, the method posits that by systematically collecting empirical, that is, observable data, one can deduce accurate conclusions about the natural world. To repeat, the scientific method posits that you collect observable data, and you take the data and interpret the world you see in the context of those data. So typically one begins with a question. It's often, well, how does that work? Or why is it that way? And then based on what's the available data and current theories and your own thinking, one proposes a testable hypothesis to answer that question. So the hypothesis would be the answer to why that biological system behaves that way is, and I plan to test it in the following fashions. So our hypothesis is not a dream, and it's not whimsical. It's based on what's known and an extension of what's known with new ideas. And above all, it must be testable with empirical data, that is, observable data. So the scientific method is empirical, and it's deductive. What those comments mean is scientists collect and analyze data, then deduce conclusions about the natural world. Those conclusions reflect the ability of technologies today. And as we evolve, as we advance in technologies, then, of course, how much the level of sophistication that we have in our understanding of the natural world grows. I'm astonished as I look back at what was known when I started as a scientist and physician and what's known now. It's just mind-boggling how much progress has been made and how much more detail we have about how our world works. It's really quite remarkable. The second topic I want to introduce is the importance of controlling systems and introducing single variables. Most of science is engaged in trying to understand how complex systems work. We are a part of a universe that's infinitely more complex than we can possibly understand today, maybe infinitely more complex than we will ever understand. But if you look at a single cell, you see a universe that's infinitely more complex than we understand today. And maybe at some point we'll conclude that it's too hard to understand for simple human beings at any level. Who knows? So these are complex systems. And the question then is, how best understand a complex system? Well, the most effective approach has proven to be to control all the variables that are possible, have as much control of that system as possible, and introduce a single change. A change is a variable. To introduce a single change into a complex system, hypothesize the potential effect of that single change, and then measure it. That is sort of the extension of the scientific method, and it's what we practice in science constantly. In the biological sciences, it is by far the most important approach that we have to understand how things work. And we have developed all kinds of different approaches to do that. Unfortunately, or fortunately, depending on your perspective, it's almost impossible to do that in humans, to deliberately introduce a single variable into a human and then ask what goes wrong. To avoid the unethical character of what I just described, we've developed a lot of cell and animal models that help us do that. While we use those animal models at great cost, billions and billions of dollars a year, all of us understand that the animal models that we have, even the best transgenic human animal models, are poor surrogates for human beings. In a perfect world, we would have humans who have a negative variable introduced, and it's a single variable that we can then ask questions about. The humans who fit that description, nano-rare patients. Nano-rare patients have a single, definable, understandable mutation or variable that's introduced that is driving these enormous changes in phenotype. And so if we can understand that patient, we understand a lot about how human disease takes place. Orthogonal thinking. Of course, there are many sources of innovation, but in my mind, the most important source of innovation derives from orthogonal thinking. And to think orthogonally, one must look at an object or a system or a process from a perspective that's different from others. A great example of orthogonal concepts has to do with vision. Plato, who did some good things, and he caused some sheer problems as well, in ancient Greece, concluded that we see by emitting rays from our eyes that we then measure as we see objects. Vision is an active process by us emitting rays from our eyes. That concept dominated the theories of vision for centuries, at least in the West. And it was not challenged until the 17th century when data showed that it was quite the opposite. Our eyes gather rays reflected from objects. We don't emit anything. We collect rays. So it was completely backwards. And that was somebody looking at the data in a different way. And it's also an interesting example to use because it shows how backwards dogma can be, but it also shows that it wasn't silly. I mean, it wasn't dumb of Plato to think that maybe vision stems from your eyes being able to emit rays. If he'd actually been studying bats, he'd have been right, because bats do emit rays, X radar, and they see the world that way. Yeah, Plato was wrong about us, but should he have studied bats, he would have been truly brilliant. So key point, the most effective way to better understand any complex system is to introduce a single change or variable and assess the impact of that variable on the system. Because it's typically impossible or unethical to introduce a single, certainly negative variable into humans, for many diseases we've had to use cells and animals as surrogates for human beings, and they all have significant limits. Nano-rare patients represent a truly unique opportunity because in nano-rare patients we have a single gene mutation that is understandable, that has been introduced into that human, that is driving significant phenotypic change. And so nano-rare patients represent a truly unique, never before encountered opportunity to learn in the right animal system, human beings. With that base laid down, I want to talk about what a unique moment in history we occupy. And that's what presents such a remarkable opportunity to us at n-Lorem. Rapid advances in actually multiple biological disciplines now provide these unprecedented opportunities to learn about the molecular architecture and dynamic molecular events that result in phenotypes that humans display. Whether it's a healthy phenotype or a disease phenotype, it's a phenotype, and we have the tools today to begin to understand why those phenotypes are expressed at a level we never had before. One of the major innovations is genomics. And every one of these innovations is a product of decades of work. Don't think of the genomics as a revolution that happened just recently. It began with Watson Crick in 1954. And so each of these demonstrate the value of long-term investment in basic science. Genomics. Clearly, because of genomics, we now know that pathogenic disease-causing nano-rare mutations exist. We're the first generation to actually know that there are nano-rare diseases. It's pretty remarkable in itself. And these nano-rare mutations represent an opportunity to learn that's unprecedented because each nano-rare mutation is a definable molecular event. And we can understand it, and we can then use that to help us understand how this single variable, this mutation, actually drives an enormous change in phenotype in the animal model that matters most to us, ourselves. So not only does a nano-rare mutation change the phenotype, but even though these mutations may present at birth, and that mutation isn't changing one iota throughout life, the phenotypes change. And so not only can we understand how that variable resulted in a change in the phenotype, we can also watch the evolution of abnormal phenotypes over time in a human being. Of course, many of our nano-rare mutations don't even manifest as diseases until later in life. So we often have the opportunity to study patients who have a mutation. We know it's causing trouble at the molecular level, but we do not see the consequences in the overall phenotype that we can measure for years. That means we can study that patient using modern techniques over decades to understand all the steps that took place to cause that patient to become what we think of as diseased. Our experience already, and we're just at the beginning of this, demonstrates that nano-rare mutations can be of all types. They can range from true null mutations that result in absolute loss of a protein encoded by a gene or a necessary RNA encoded, or a toxic gain of function mutation that results in the production of a mutant protein or RNA that interferes or does harm or has a new function, makes cells dysfunction. These mutations could be homozygous, that is, both copies of genes mutated, or heterozygous, one copy of the gene mutated. And we have very complicated cases in which we have, compound heterozygous mutations where two pathogenic mutations occur in different genes that produce disease. And we know that these mutations can happen in every gene, every type of gene family. They can happen not just in coding regions, but in regulatory regions and in non-coding regions. And so we already have learned an incredible amount in just a few years. The nano-rare mutation carrying patient is an extraordinary asset from which we have the potential to learn great lessons about health and disease that we cannot learn from any other source, not nearly as well. The third area of advances is advances in what I'm calling omics. Contemporaneously with the rapid advances in genomic sequencing, new molecular diagnostic tools have become available that enable scientists to better understand the molecular events that result in the phenotype observed in our patients without having to be too invasive. These are grouped into three different groups: transcriptomics, proteomics, and metabolomics, each of which is then comprised of several sub-technologies that support examination of more specific human molecular characteristics. These methods can be used, as I said, without the need to be super invasive. Transcriptomics refers to the tools that support understanding the characteristics of the RNAs in the cell. Recall that RNA is transcribed from the genome, and that there are many types of RNAs, including RNAs that code for proteins, messenger RNAs, those are called, RNAs that serve other important functions, and RNAs that carry out functions that only RNAs carry out. The RNA world is really important, and it's complex. Transcriptomics is by far the most advanced tool we have today, and it's the most precise. And it can be combined with genomics to understand what's going on in the cell. And of course, there are many sub-technologies, and they grow every day, that support even more detailed understanding of the states of various RNAs and the molecular processes that are involved in producing those RNAs. For example, there are methods to support understanding RNA in the RNAs in a single cell in detail, rather than trying to understand the RNA in a population of cells. There are also all sorts of transcriptomic processes that allow us to subcategorize RNA that's in various parts of the cell, doing various things, and so on. And so the transcriptomics facilities that we have give us incredible insights into dynamic events that are taking place every minute of every day in every cell in your body to keep you in a healthy state. Proteomics is a set of tools that support understanding the types of proteins that may be present in cells or bodily fluids or any other place. Additionally, there are sub-technologies that support understanding some of the ways proteins can be modified. For example, their key way that proteins are regulated is by adding phosphates, and so they're phosphoproteomic. Their proteins can be methylated and acetylated and ubiquitinated, and so there are all these sub-proteomic methods that allow us to subcategorize what's going on with your proteins in your cell. And then the third omic is metabolomics. And this refers to technologies that support analyses of the many small molecules that play essential roles in the maintenance of normal life and reflect, again, the output of cells in our body, and obviously reflect changes that can result in disease. These include things like hormones, electrolytes, all kinds of different metabolites that the cells of your body engage in and make that can be measured. And they can be measured in blood, they can be measured in other kinds of bodily fluids. And as a consequence, then, we can have a pretty good sense of what's going on at the RNA level, what's going on at the protein level, and how all that's integrated to drive metabolism. A lot of tools. And they're advancing more every day. Now, the major area that I want to discuss is biological networks and analysis of those networks using what I'll refer to as AI. As far as I'm concerned, AI is an overused word, but really it just boils down to trying to learn from massive amounts of data. Arguably, the most informed way to think about the appearance and behaviors that we look at in human beings, that is, the phenotypes that we observe, is that they represent the integrated output of an astonishingly complex array of biological networks. Biological networks work like networks in computers, and like networks, most individual biological responses are binary. So just like in a computer, most of your biological responses are plus minus. And yet, biological systems have to give infinitely graded responses to the environment if you're going to just survive. And so, like computers, these individual biological responses are integrated into ever more complex networks. And those networks then allow you to respond to various environmental changes with a graded response, an almost infinitely graded response. So each cell in your body is organized into, I can't even begin to imagine how many different networks. And those networks are stacked on top of one another, ever more complex and integrated. So there's a hierarchy of networks, not just that there are a bunch of networks, but each network is integrated into our higher order network and a higher order network from that and a higher order network from that. And so there's just a multiple layer approach to managing your cellular life. And then all of your cells are integrated into networks. And your organs are organs because they have their own networks. And all of that then gets put together in networks that end up describing you and me. All of the things that I talked about, RNA, DNA, proteins, metabolites of all sorts, are all participants in these networks that integrated into what we see as phenotypes. Of course, we're organized into organs to help us create these broader networks that are organ networks, and then those organs are integrated into the whole organism, which is you and me. We've known that these networks exist for a long time, but we're only now beginning to have the computing power, the tools that allow us to actually understand how a change in one component of this network might influence a network many orders of magnitude away and more complicated network. And we have the tools to do that thanks to just computing power. The fourth item that I think is really important and we use every day at n-Lorem is the ability to collect, maintain, grow, and differentiate human cells in the lab. I just can't emphasize how fundamental this advance actually is and how it would be almost impossible for n-Lorem to work if we didn't have this. We certainly would be unable to treat patients and we wouldn't be able to treat them with the confidence that we have if we were not able to collect skin cells or blood cells and then use those cells and then in the lab, grow them, maintain them in the lab, and then differentiate them into various types of cells like neuronal cells or liver cells or kidney cells or whatnot. It's that ability to collect those cells without having to be invasive and maintain them, grow them, and differentiate them into various types of cells that makes so much of the work that we do every day possible. That technology is called inducible pluripotent stem cell technology. And that really just means we can induce these cells that have multiple potentials to differentiate into specific types of cells. And you'll see that abbreviated with a little I, capital PSC. And again, all that means is we collect fibroblasts or blood cells, we grow them up, and then we can differentiate them in the way we want to whatever type cells we want to study. And that allows us to study the phenotype of the human cell with the mutation that our patient has in context and ask, what is the phenotype, and does our ASO correct that phenotype? I just can't emphasize how important that is, because for the first time, we can then use all the tools that we have in human cells with the mutation that human expresses to understand the molecular architecture of those cells, what that mutation does to cause things to go awry, and we can use the same cells to tell us if our ASO can fix all the problems that mutation causes. Nothing could be more important than that. If you couple all that I just described to a technology that works effectively and rapidly to create mutation-specific treatments, you really have something. That's called n-Lorem. Because the fifth major advance is Antisense Technology. And like all these other advances, it's a product of decades and decades of work, and it's still advancing. And so thanks to more than 3 decades of work, primarily at Ionis and now at n-Lorem and other places, we have the technology to take advantage of the knowledge about these mutations and rapidly create genetic therapies that address the genetic cause of nano-rare diseases and rapidly move those genetic therapies into the patient. And so for the first time, we can understand the nature of the mutation. We can understand the impact of the mutation on the molecular architecture of the patient's cells that are the problem. We can then use ASOs to correct the defect, measure the impact of that correction in those cells, then take that ASO and put it into human beings and measure the effect on the human phenotype, all in a short time. And so for the first time, we have this extraordinary ability to learn. And knowledge is power. And what we are learning is informing us about health and disease that goes well beyond what we think of as nano-rare diseases, while we enable nano-rare patients to lead a better life, to lead a longer life. And we enable nano-rare families to have hope and to be able to look to a future with a great deal more optimism and confidence than they might have before n-Lorem. That's pretty good. And we wouldn't be here talking about this if it weren't for billions of dollars invested over many decades in the basic sciences that inform us about who we are, what goes wrong, and how to fix it. So at our next podcast, then, I'll finish Knowledge is Power and discuss what kinds of questions we're able to answer today and how much more we'll be able to answer if funding were sufficient to address some of the many interesting questions that go beyond what we can do today because of limited dollars.
Can you believe it's been 2 years since we started this podcast journey together? We want to hear from you on how to make the Patient Empowerment Program podcast series an even better resource for nano-rare patients. Please consider giving us a few minutes of your time to complete a survey on our podcast. As a thank you, you'll receive a special coupon code to the official n-Lorem Foundation store. You can access this survey by using the link in the description. Your feedback means a lot to us.
n-Lorem is a nonprofit committed to discovering and providing personalized experimental treatments for free, for life, to patients with genetic diseases that affect 1 to 30 patients worldwide, referred to by n-Lorem as nano-rare. Many of these patients progress and die without ever achieving a diagnosis. This is where n-Lorem comes in. They do the impossible by providing hope, and for those that they can help, free lifetime treatment. For more information about n-Lorem or today's episode, visit n-Lorem.org. Any questions can be sent into podcast@n-Lorem.org. Search n-Lorem on Twitter, Instagram, YouTube, LinkedIn, and Facebook to connect with us. Please rate and review the podcast on Apple, Spotify, or wherever you listen. This truly helps us climb the charts and allows others to find the show. This podcast is hosted by Dr. Stan Crook. Our videographer is John Magnuson of Mighty One Productions. Our producers are John Magnuson and Kira Deneen of DNA Today. Thank you for listening.